Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is on clustering. It's part of the course Analytic Methods for Lawyers, but again, like many of the videos in this series, it really can be used by a broader audience. Clustering is a form of unsupervised learning. Unlike supervised learning, we no longer have targets that correspond with the features. Really, all we have is the features. And what we want to do is to find out about the relationship of the features to each other. Clustering is just a way of saying what forms of data are like another. I'm going to show three methods of clustering in some detail here: KMeans, KMedoids, and the Jarvis-Patrick method. I'll show you how they and other methods are implemented in the Wolfram language, and I'll finish up by showing how clustering can be used as a predicate to classification. Let's start with KMeans. KMeans is probably the most commonly used method of clustering, and it has the virtue of being pretty easy to understand. So let's start with some one-dimensional data, and I'm going to build it so that it does really have clusters. That is, I'm going to draw 20 values from one distribution, 20 values from a different distribution, and 20 values from a third distribution. I'll seed our random number generator so we get consistent results. And here's our data. We can use number line plot to see how those points are distributed. So there they are. Maybe there's a cluster here, maybe there's a cluster here, and there's this kind of the clump in the middle. That's the eyeball method of clustering, which frankly the human brain is pretty darn good at. But let's do it a little more mathematically. Let's make a guess as to where the center of three clusters of data are located. Nothing magic about 3. I could pick 2, I could pick 5, I could pick 6, but just some integer, and that integer k is the k in KMeans. And I could pick any points in the world, but I'm going to pick 3 points that are actually in the data set. There are some technical reasons why that can help with stability. So there are my 3 random points. All right, now let's take our centroids. Let's just get the values of them, so we just get these numbers. And then let's build a function that if I give it a value, it's going to say which of these centroids is it nearest to. So if I give it 1.3, it's going to say, oh, you're near centroid 2. And if I give it 0.21, it's going to say, oh, you're near centroid 3. All right? What does this all thing do? This all says I want a lot of information spit back about what's nearest. I want to know what is the actual value that it's nearest, what index is it, and how far away am I from it. So there we go. We have our little nearest function. And just so you see how it applies, here I'm going to ask for the 2 values nearest 0.44. And it turns out that number 3 is the nearest, and number 1 is the next nearest. Here are the distances, and here's what those elements are. If I just want the closest element, I can compose application of my nearest function with first, and there we go. And if I want the index, if I want to know, hey, what numbered cluster centroid are you nearest, I can just again compose index with this. And it tells me, oh, at 0.44, you are nearest to number 3, because 0.44 is pretty close to 0.23. All right, so now here's what we're going to do. We're going to take all of our data, and we're going to find out what is the index number of the centroid that it's nearest. That will help group the data into different categories. It'll be grouped depending on what centroid it's nearest. And then, for each grouping, we're going to compute the mean value of the data within that grouping. That's what this MapReduce operator does. And so here we are. We have 3 new values. And those are the new centroids. Okay? And I can do exactly the same thing that I did before. I can make a new nearest function and say, now, for any point, which of the new centroids are you nearest? Okay, and I have a new nearest function. Before we go any further, it's time for a little digression on a Wolfram Language programming construct called so and reap. Remember that Wolfram's a functional language, generally speaking. You usually take input and you produce output, and usually you try not to change the state of other symbols along the way. But sometimes it's helpful to preserve some interim computations you made along the way, and using so and reap is one idiomatic way of doing this. So let's look at an idea. Supposing I have a function, f, and what I really want is for it to compute x cubed. But maybe I might also want it to compute x squared. And maybe I don't want to have to go through the whole effort of doing it again. Maybe I just want to store it. So the way I'm going to do that is I'm going to say so, like so in the ground, x squared. Now, if I now execute the code f of 5 and I don't say anything about reap, the little seed I sowed in the ground is never reaped, and I just get the same thing that I would have gotten if I'd never sown the seeds in the first place. But if I enclose my function call in reap, now I get not only the answer, but I get a second part, which is a list containing a list that has every time that I sowed. So it's 25 and it's wrapped in a double list. One thing I can do is I can do a simultaneous assignment. I can say, let regular and reaped be the reap of f5. And so now, if I say, hey, what's regular? Regular is 125. And if I say, what's reaped? Reaped is list 25. Okay, digression over, back to business. Let's write a function that automates this process of taking data, taking the old centroids, taking an agglomeration function, which by default will be the mean, will form the nearest function based on the existing centroids, will sow that nearest function in case we might want it at some later date, and then we'll compute the new centroids using exactly the same technique I showed you up here. Okay? So that is our evolve centroids function. And now what I want to do is I want to iterate application of evolve centroids a lot of times. I'll start with the initial centroids, I'll evolve new centroids, then I'll take those new centroids and I'll use evolve centroids on that, then I'll take those new centroids and I'll use evolve centroids at that, and I'll do that up to 20 times, but I will stop if the centroids ever stop moving. This basically means the centroids have moved one part in a million, and that's enough for me to stop. I'll reap what I've got, so I'm going to get all the nearest functions I obtained along the way. Right? So we're going to run that, and here's what we get. Here's the first time value of our centroids, here's the next value of the centroids, next value of the centroids, and here are the 1, 2, 3, 4, 5, 6, 7, 8 nearest functions I generated during the 8 iterations it took for the system to converge. Well, one thing I can do is I can actually plot the trajectories of the centroids. And to do that, I've got some code here. I don't think it's particularly instructive for me to go over that verbally with you. Just know that what I'm going to do is I'm going to take the trajectories here, that's FPL. I'm going to convert those trajectories into arrows. I'm going to color the arrows, and then I'm going to make a picture out of it. All right, so there we are, and here's the trajectory of the centroids. And as you can see, there's a little instability where they're crossing each other, but ultimately they're going to stabilize. The system is going to stabilize. Moreover, if we want, we can look at how the points fit into the various regions that are defined by the evolutions of the system. Again, this is some little bit complicated code. This is just to have a nice colored number line plot, and this is working with those reaped nearest functions to do the coloring without having to recalculate everything. And you can see it does work super fast. And so here's what the clustering looks like on the first iteration. Here's the second iteration. You can see a big change. Third iteration, big change, and we're beginning to stabilize here. And by the time we're getting to the 5th, 6th, 7th, and 8th iterations, not too much is happening, and in fact, between the 7th and 8th iterations, nothing happens, and so the iteration stops. Well, this was the trajectory if I just picked some random initial points. Here were the random initial points that I picked. But maybe changing the random initial points would change the trajectories and would change the clustering. So what I'm going to do next is to come up with 20 different examples of initial points, go through the evolution, and let's see what happens. All right, it did it. And now what we're going to do is we're going to make a picture showing the evolution. And you can see that although they do fall into basins of attraction, like the blue arrow never seems to end up over here, and the green arrow never seems to end up over here, nonetheless, the centroids don't end up in exactly the same place. So different basins of attraction that we fall into depending on where exactly the initial placement was. Now, maybe the difference between these points is so insignificant that it ends up not making any difference in the actual clustering of the points. So let's test this. And what we're going to do here is I'm going to see on what fraction of the occasions, of the 20 occasions, are 2 points in the same cluster. So if the initial value never makes any difference, then 100% of the time the 2 points will be in the same cluster. And for example, it looks like 0.1 and 0.21 are always in the same cluster. Maybe they're so near each other that doesn't make any difference. And similarly, it looks like maybe 0.1 and 0.2 are so distant from each other that they're never in the same cluster. Just don't worry about the ones and ones. All the diagonals are listed as 0 because they're always in the same cluster, and probably it should be a 1, but don't worry about it. But in any event, what you see here is actually some structure to this matrix, and this structure reflects the fact that my initial points were ordered. They were coming from different clusters. But what you should also see is there are a lot of instances in which it all depends, like 0.1 and 0.43, or 0.30 and 0.19. It depends on the initial values, and so the clustering is somewhat arbitrary. It depends on the initial points. This, I would say, is a major big picture point, is that clustering is often non-deterministic, even if you're using the same algorithm. And so you can't just rely on a single picture and say definitively that 2 points are in the same cluster. That was K-means in one dimension. But can we do it in multiple dimensions for multi-dimensional data? And the answer is not only you bet, but we can do it with really exactly the same code. So let's build a 2-dimensional data set here. Same idea, drawing from 3 different distributions. And you can maybe make out the 3 sort of clusters here, I would say. But let's see what our little computer has to say for it. This is essentially the same code as before. We're going to evolve our centroids by figuring out which centroid each point is next to. The points that are so grouped, you then compute the mean position of that grouping. That becomes the new centroid, and you play the game again. All right, there we go. And what I'm now going to do is to do that same evolution of trajectories thing. Here's what our grouping looked like. Seems like a reasonable clustering to me. And you can again see, though, that exactly where we end up can depend significantly on the initial points we picked. So this is the X and Y locations of the centroids, the 3 centroids that we find. All right, so that is K-means, a very influential algorithm and one that it doesn't really take that much code to execute. Let's talk about KMedoids, and frankly, I've never heard anyone say the word, so I hope I'm pronouncing it correctly. All right, it's almost exactly the same thing as K-means. The only difference is that to agglomerate the points that are closest to the same centroid, instead of using mean, you use median. Get the medians of the values. So there we go. And we can do the same thing, and we can do the same analysis of whether the trajectories go in the same, whether the centroids end up in the same place or whether there's vulnerability to the initial value. And you can see pretty clearly that there is vulnerability to the initial value. So KMedoids provides an alternative method of clustering. I'm not saying it's better or worse, but I am saying that it does have this problem that the clusters that it determines depends on the arbitrary initial selection points. All right, well, you've seen how to do home-brewed K-means and K-medoids. Maybe you're thinking it's like often is the case where Chandler first shows you how to do it by yourself and then shows you that actually there's an easier way. And there is. Now that you understand what's going on, now we can use magic. So the Wolfram Language command you need is find clusters. Here's how find clusters work. You give it the data. For many methods of clustering, you tell it how many clusters you want, and then you can, if you want, specify what method you want to use. Here I'm going to use K-means first, K-medoids second, and then I'll make a plot here showing the clustering. So here it is, and you can see it's similar, but not identical. See how here with K-medoids, the blues have made inroads here, whereas with K-means, the greens were holding out. And it also looks like the greens maybe are doing a little better here than they did with K-means. All right, but that's the command. Find clusters, tell it what your data is. For many methods, you do need to tell it how many clusters you want. For other methods, you can't tell it how many clusters you want. It insists on figuring out itself. And what method you want to use. If you leave out the method, Wolfram will figure out the method it thinks is best. Find clusters has a cousin. Supposing instead of grouping the points, which is going to be the output of find clusters, you want a list of to what cluster does each point belong. The command is clustering components, and it's basically the same syntax as find clusters. And this is telling us, okay, point 1 belongs to cluster 1, the last point belongs to cluster 3, the second to last point apparently belongs to cluster 2. And again, you can give it a method option, and so here the clusters are not identical. Like if we look at the second to last point, for K-means it belongs in cluster 2. For K-medoids it belongs in cluster 3. Right? But that's how to implement this in Wolfram Language. It's find clusters if you want a list of points coming out, and it's clustering components if you want a list of what clusters it belongs to coming out. See what the Jarvis-Patrick clustering looks like. So here it is. If I start to change the radius in which I'm looking for friends, you can see that I'm beginning to change the number of clusters that I have. I'm sorry, that's changed the fraction. What if I change the radius? I've got, well, it's interesting. What if I change the maximum number of friends I have? In any event, you can play around with this, and one of the things you see is that Jarvis-Patrick clustering suffers very much from the same dependence on some parameters that K-means did. It's deterministic once you have the parameters, but the choice of parameters affects greatly the type of clustering. Again, you never have to do this again. You can just say find clusters, method Jarvis-Patrick. And there you go. Okay? You should also know that it accepts sub-options. So if you want to change how far you look or how many neighbors you need before you consider yourself to be in the same group, there you go. You should also know that Jarvis-Patrick has a cousin named Spectral. And I did not go through spectral with you because it involves some pretty heavy-duty linear algebra with eigenvectors and the like. And while I have used eigenvectors on occasion, I kind of get a little nervous about that. And spectral, let's see what spectral does. But it relies on the same notion of there being an underlying graph of connectivity between people. And one virtue of spectral is that it gets this one exactly right. Now, there may be lots of other problems where spectral doesn't perform as well, but at least on my particular problem, spectral accords with human intuition. Well, in the past, I've had to tell Wolfram how many clusters I want, but could I just let it figure it out on its own? And the answer is yes. Some methods don't require you to specify a number of clusters, and you just leave that out. And so, here's our original data. I haven't told it to make 3 clusters, but it thinks that 3 clusters is about right. I can't say I'm super impressed with the clustering it did here, though. Like putting these reds together with those reds, whatever. Like I think it would, let's see what happens there. Okay, I guess it's finding up to a maximum number of clusters. In any event, that's the default behavior when you don't specify clusters. There's more arbitrariness. What I've done here is this, I've taken this graph from the documentation, and what it does is it shows, okay, here's the same data, and here's how all of the methods that Wolfram knows about, how it clusters them. For this data, this is easy data. It looks at all the same. This data, again, mostly the same. Now we get 3 stripes, and we start to see differences, where to me it looks like Jarvis-Patrick spanning tree mean shift are getting answers that accord with my intuition, but not KMeans, KMedoids, agglomerate, or dbScan. For this piece of data, I like dbScan, spectral, Jarvis-Patrick, and spanning tree. I'm not big fans of the rest. Agglomerate does correct. The one that seems to always get my intuition right is their version of Jarvis-Patrick, and their version of spectral bungles this one. So they've put in parameters to Jarvis-Patrick that get it to work well. The main point, though, is, again, what you say is clustered with what other point depends on what algorithm you're using and what parameters you're giving to that algorithm. Let's talk about supervised learning with clustering. One thing we could do would be to take some initial points, cluster them, and have that clustering algorithm figure out the boundaries where if in the future another point comes down, it will assign that point to one of the clusters. This is sort of a form of semi-supervised learning, and we can create a cluster classify function. We can now apply that function to a point. It says, oh, that point's in cluster 2. Or we can throw a lot of points at the cluster, the classifier. Here I'm going to throw 5,000 points at it, and I'm going to color them according to what cluster they're assigned to. And so you can see, basically, here's the boundaries of the classifier that was created not by using 5,000 points, but just by using RV Nasty, which I believe had 100 points in it. Again, what your boundaries are depend on what method you use for clustering. Same data, but now I'm using spectral method rather than what I used up here, which was, remind me, Jarvis-Patrick. All right, so let's use spectral. We get a classifier function, produces 13 classes, and here's its boundaries, which are clearly more complex than those created by the Jarvis-Patrick method. So, what's the big picture? The big picture is clustering is a useful unsupervised learning tool, but you've got to view its conclusions with a critical eye, because what cluster gets aligned with what depends not only on the clustering algorithm you use, but often on the parameters to that clustering algorithm, the number of clusters selected, and in some cases just on random initialization. You can use clustering for classification as I just showed you, but the results from that are as brittle as is clustering generally. I think this is an important lesson to learn not just for technical data analysis, but actually for life. In life, for example, we tend to cluster people by race, by gender, by other categories, and often that is useful. It's not a meaningless exercise. But we ought to recognize that clusterings in those fields have the same elements of arbitrariness and contingency as they do in the technical analysis we provided here. Thanks a lot, and I'll see you in the next video.